So in the previous class we have discussed the features of the compensator in terms of the power factor correction and the voltage regulation. We have seen that if we control the power factor, then voltage cannot be controlled independently. And although voltage improves out of the correction of the power factor, but its value is not controlled by us, or its value is not controlled by the compensator. It comes as a consequence. Similarly, we have seen that if we regulate the voltage, then we cannot control the power factor. Now, there are two aspects for the compensator. Number one, what should be the value of Q gamma for which the compensator has to be designed, and second thing, what must be the rate of change of reactive power of the compensator with respect to the voltage. In other words, when we design the compensator to meet these features, that is the power factor control or the voltage regulation, then we must be able to find out what must be the maximum rating, that is S gamma max, which is same as Q gamma max, because there is no real power. Second thing, at what capacity, at what rate this reactive power of compensator can change as a change or as variation in the voltage, that is dQ gamma by dV. So rate of change of the compensator reactive power with respect to the change in the voltage and also its maximum capacity. These points are discussed in section 4.2 of the NPTEL book. Please go through it. There is one example I am not discussing here. It is a simple example so you can understand by yourself. In the next part, we are focusing on the three-phase unbalanced system and how these three-phase unbalanced system can be compensated. In the beginning, we will focus on three-phase delta connected load or three-phase star connected load without neutral grounding or without neutral grounding, not ungrounded. This is, please correct it. So this is not the correct thing here. Without neutral grounding. Let's cut this part. So in this case, now the focus is on load compensation for three-phase unbalanced system, and we will first consider three-phase delta connected load or three-phase star connected load without neutral grounding. If you ground the neutral, then it becomes three-phase 4-wire system, and that is an entirely different scheme. So we will first focus it for three-phase delta connected system. Okay. So even though these kind of loads are not very common, but study is quite useful in order to understand the compensation techniques. Now let us first review the equivalence between the three-phase star connected load and three-phase delta connected load. So this is three-phase delta connected load on the left hand side of the figure, and we have shown it by gamma AB, by gamma BC and by gamma CA, not gamma, by L, by LAB, by LBC, by LCA. L for load and AB means between A and B. So on the delta side we have by LAB, by LBC and by LCA. Now if we convert into equivalent star, ZA, ZB and ZC. You know this equivalence with the help of circuit theory, you can find out the equivalence between the star and delta, and you can recall that these values are ZA equals the multiplication of ZAB and ZCA. If you want to remember, it's very simple. If you want to find out this impedance, multiply these two branches, this and this, side by branch. So this is YLAB, YLCA, but not in terms of the admittance, but impedance. In terms of impedance, we can write them as this is 1Y ZLAB, this is 1Y ZLBC, 1Y ZLBC, and this is 1Y ZLCA. Then ZA equals to the multiplication of these two branches divided by the sum of the impedance, that is ZAB plus ZBC plus ZCA. Okay, these are the summation of the three impedances in delta connected load. This can also be written as ZAB ZCA by sigma ZAB. Sigma means ZAB plus ZBC plus ZCA. Sigma ZAB means ZAB plus ZBC plus ZCA. Similarly, we can find out ZB. Similarly, we can find out ZB, which is ZBC into ZAB divided by sigma AB. And likewise, we can have the ZC, which is equals to ZCA into ZBC divided by sigma ZAB. Also, we can express the star to delta. In star to delta, we are given ZA, ZB and ZC. And we have to find what is ZAB, what is ZBC, what is ZCA. In that case, we have to find sigma ZAB, which is sum of ZA, ZB plus ZB, ZC plus ZC, ZA, and divide by the ZC. Similarly, we can find out ZBC, ZCA. So this equivalence, you might be knowing it. For the sake of completeness, I have reviewed this equivalence between the star and delta connected load. Now, if you want to solve three-phase system and find out the various components of current and powers, they are slightly difficult as compared to three-phase four-wire system. The reason is, in three-phase three-wire system or three-phase delta connected load or a star connected load without grounding, the neutral is floating. So neutral is not at zero potential. Because of that, the current involves the computation of the neutral voltage. And hence the calculations are a little tricky as compared to three-phase four-wire system. For example, in this figure which you see on the right hand side, three-phase three-wire system, where it carries the load currents IA, IB, IC. This is IA, this is IB, this is IC. For the delta connected load as YLAB, YLBC and YLCA. We can express the voltage which are supplying this load. So these voltages are expressed as BA, BB, BC. Where are these voltages? If you want, you can connect here. This is BC here. This is BB. And this is BA. So BA, if you want to write in terms of the phasor, we can write in terms of phasor because it is only fundamental frequency component. So this is BA, this is BB, and this is BC. And you can join them by a neutral. So these voltages can be expressed as B angle 0, B angle minus 120 and B angle 120 degree, because they are balanced. Voltages are balanced. Only the load currents are not balanced because ZAB, ZBC, ZCA are different. Now this minus 120 can be expressed as alpha square or A square, and 120 degree can be expressed as alpha. We have defined this alpha and alpha square as a complex operator which is giving a complex variable having the value of alpha as or A as one angle of 120 degree, and alpha squared sometimes we denote as A square one angle of minus 120 degree. Correct? And we know 1 plus alpha square equal to 0. Alright, so with this notation of phase voltages, we can compute the line currents. Now how to compute line currents? Before we compute line current, we must know what are the line currents. So what is IA, what is IB, what is IC? Well, IA, IB, IC can be expressed in terms of the phase currents IAB, IBC, ICA. So what is IA? We will apply Kirchhoff current law at this point. That is, IA will be equal to IAB minus ICA. So this is IA. And then we have a IB, which is IBC minus IAB. And IC is ICA minus IBC. So these currents are found by applying Kirchhoff current law at point A, B and C. And what is IAB? IAB is the current flowing from point A to B, this current. Obviously, this current must be equal to, so BAB into YLAB or BAB by ZAB. This is the current ILAB. So currents are expressed as IAB as BAB into YLAB and IBC as BBC into YLBC and ICA as BCA into YLCA. Now we substitute the value of BAB. BAB nothing but BA minus BB. Am I correct? So this is BA minus BB. BA is simply B because B is the reference phasor, as you can see from this equation. So this is simply B, and BB is nothing but alpha square because this is minus 120 degree. So this is alpha square. Therefore, BAB becomes 1 minus alpha square. Okay, so this is 1 minus alpha square. What is BBC? BBC is BB minus BC. Now B is alpha squared, C is alpha. You can see from here, this is alpha squared minus alpha. So this becomes alpha square minus alpha B. What about BCA? BCA becomes BC minus BA, and BC is alpha, A is 1, so alpha minus 1. So these are line to line voltages in terms of the voltages value Vrms and complex operator alpha. You can also see that for this system, the three phase currents, if you sum them, IA plus IAB plus IC, it will be equal to 0. It is obvious because if you apply the Kirchhoff current law for equivalent delta star connected load, okay, there is no fourth wire where the current can go. For example, if we transform this circuit into star, it will be like this. this is star, and okay, you can take any A, B and C, any order, like this is A, this is B, this is C. Then you see this current is IA, this is IB, and this is IC. Now there is no fourth wire. The fourth wire is broken here. It's not there. Therefore, the sum of three currents will be equal to 0. In other words, there will be no zero sequence current, or there will be no current in the fourth wire. And you can see from here also, if we add these three parameters, this will go with this, ICA will go with this ICA, and IBC will go with this IBC. The summation of three currents are equal to 0. So in delta connected node, there is no zero sequence current. Now we can express the line current in terms of the voltage B and the admittance parameters. Okay, here it is some problem, so I will just change it. This is alpha actually, and this you have to change it, alpha square minus alpha, so this is actually alpha. Now we can express these currents using these voltage relationship shown here, AB, BC, CA, and this relationship. So what is IA? IA is IAB minus ICA, and IAB is BAB into YLCA, and BAB is BA minus BB, 1 minus alpha square B. Substitute all these values to find out the current IA. So IA becomes BAB into YLAB, and BAB is 1 minus alpha square B. So this is the BAB, this into this, and this is YLAB, minus ICA. So ICA becomes BCA into YLCA. Okay, so this is YLCA, and BCA becomes BC minus BA, which is alpha minus 1. So this is alpha minus 1. Similarly, IB is given as BBC, alpha square minus alpha into YLBC, minus AB. So AB becomes A minus B, that is 1 minus alpha square into YLAB, and B will be here. For C, it is BCA into YLCA, and BCA is nothing but IC is BCA into YLCA, BCA is alpha minus 1, minus BBC into YLBC, and BC is alpha square minus alpha. So these are the currents, that is line currents in terms of the RMS value of voltage, as you can see here. Okay, and the admittance parameters along with the complex operator alpha. If we know the load admittance and the RMS value of the voltage, we can find direct line currents. This is one way of computation. The second way of computing the line current is using the mesh method. You can also write the mesh equations. For example, you can write, this is one equation, okay, then you write second equation, and then third equation from here to here, and you can solve for these three meshes. We can also use one more method by applying the Kirchhoff current law. I will talk about those in the coming classes. Now after this, what is the next step? The next step is to understand that if we take three-phase unbalanced system, what is the possibility of compensation, and whether it is possible to make the load to behave as a balanced load with the help of the compensator. So in this section, we are considering a three-phase unbalanced system. In fact, we are considering three-phase unbalanced system with maximum unbalance. So what do you mean by maximum unbalance? It actually means that this is the maximum unbalance possible in three-phase system, and this example is similar to what we have discussed earlier. Earlier we have discussed like this, that there is a one point A and point B, point C, point N. N was open and we have connected resistance between A and B. This R was between A and B. This example is similar to that. So earlier we have taken one example where we have considered resistance connected to point A and B, and C and N were open. Now this example was similar to this. We can think of a delta connected load where a resistance is connected between point A and B, you can see here, and between A and C and B and C there is no admittance, or there is an infinite impedance. Let us say that we denote the admittance of this network as YLCA equal to GLAB, which is equal to 1 by R. So this is nothing but actually 1 by R. And YLBC is 0, YLCA is 0. So this is the example of an extreme unbalance in three-phase system. Now let us find out these currents. IA is given as minus IB equal to BAB by impedance, and BAB is nothing but root 3 angle of 30 degree by R. So actually this is nothing but BAB into YLAB. What is BAB? BAB is root 3 B angle of 30 degree. And what is YLAB is 1 by R. IA equals to minus IB because if you write the KVL and see this path, this is the direction of current, so it goes like this. Since this is 0, this is 0, so IA return back to phase B, and hence IB equals to minus IA, or IA equals to minus IB. IC is 0, there is no flow of current in phase C. Okay, so you see that there is a unbalance in the circuit. The currents are very much unbalanced. The C phase current 0 current, A and B phase carries the current which are just opposite to each other. So there is no balance in terms of the magnitude or phase angle. Now the question is that can we made this system to behave as a balanced three-phase system by connecting a purely reactive network. So let us say this possibility, how it is possible to make this load to behave as a balanced three-phase system by connecting a purely reactive network. Now let us start with some assumption, with just some value. Of course, there is a logic for that value. Okay. So let us say that we have compensator, and compensator is connected between point A and B, between B and C, and between point C and A. Let the value of these compensators be Y gamma AB as 0 here, Y gamma BC is J GLAB by root 3, and YLCA equals to minus J GLAB by root 3. Assume that these are the values which are connected across point EB, BC and CA for the compensator. Basically, we are connecting a capacitance here because this is the positive susceptance. A capacitance has a positive susceptance value, and this is an inductance because this is a negative value of susceptance. A susceptance with a negative value is basically inductive load. Now, if we combine these two, if we combine the load and compensator, so this was the load, this is the compensator, load plus compensator, because we are connecting the compensator across this. So this is by gamma, this is by gamma here, this is by gamma BC here, and this is by gamma CA here. Across each point we connect the compensator. So this is Y gamma AB by gamma BC by gamma CA. If you look from the supply side, you will see this circuit. Okay? You will see a resistance between point A and B. Then you will see capacitance between B and C. And you will see inductance between C and A. After compensation, we will see this circuit from the supply side. Now we want to study this circuit, how it looks from the supply side and what are its currents. So let us solve this compensated three-phase circuit and try to find out the currents. To find out currents, we must know the admittance, the total admittance, and then we can put these values in the expression that we have developed earlier, or we can also find out using the mesh method or nodal method. We will see it. Now, what is the total admittance including the compensator? The total admittance is nothing but sum of bi L AB and bi gamma AB. Since bi gamma AB is 0, therefore Y total AB is GL AB. This is 0. Similarly, for Y BC total, it is sum of YL BC and Y gamma BC. Now, this is 0 in this case, and this is J GL AB by root 3. So the total admittance is J GL AB by root 3. And for CA, we have bi L CA plus bi gamma CA. This is again 0. And Y gamma we have chosen as minus J GL AB by root 3. What is the behavior of this circuit? So we want to try with these values, that's all. How they have come, that will be explained in the coming classes. Alright, so with this admittance, we can find out total impedance for each branch. So ZAB will be 1 by YTAB, that becomes 1 by GLAB, and ZBC becomes 1 by ZLBC. Actually it is T total. This is also total, so you can put T here if you want to put. And therefore we will get this value as minus J root 3 by GLAB, and Z total CA as 1 by total CA, which is J root 3 by GLAB. So that's how the circuit looks. Now from this ZAB, ZBC, ZCA, we can find out the star connected equivalent ZA, ZB, ZC. So these three values will give us ZA equals to ZAB into ZCA by sigma ZAB. Substitute these values, you will get sigma ZAB is nothing but sum of all these three impedances. So that is nothing but 1 by GLAB, because these two will cancel. So this is the value of ZAB, which is substituted here. Okay, and AB is 1 by GLAB and ZCA is J root 3 by GLAB. This will cancel both the sides and you will get only J root 3 by GLAB. So this is the value of ZA, and then we find out the value of ZB as minus J root 3 by GLAB, and then ZC, which is 3 by GLAB. So now we know the total impedance of loads for phase A, for phase B, for phase C in a star connected configuration. Now with this configuration, we will find out the currents. How will you find out currents? Currents can be found out by many methods in fact, but to make it simpler and to understand better, we will use the nodal method, or we will use the neutral voltage method. What is that method? The method is this, that this current is IA, this is IV, this is IC. This is capital N, this is small n. What is the A phase current flowing? The current here is VAN minus VNN divided by Z, let us say A. Sometimes I use upper, sometimes lower. For the sake of simplicity, I put it lower here, but you can also use ZLA. So I have simplified ZLA equals to where ZA, okay, and ZLB equal to ZB, for example, and ZLC equal to ZC. What is IB? IB will be nothing but BBN minus BNN divided by ZB, and IC will be BCN minus BNN divided by ZC. And you know that this is three-phase, three-wire system. Therefore, applying Kirchhoff current law at this point N, will get IA plus IB plus IC must be equal to 0. That implies that BAN minus BNN by ZA plus BBN minus BNN by ZB plus BCN minus BNN by ZC must be equal to 0. So we will find out what is the neutral voltage. We will take this common factor in all. So this becomes BNN into 1 by ZA, 1 by ZB, 1 by ZC will be equal to BAN by ZA plus BBN y ZB plus BCN y ZC. Okay, then we can write the expression for BNN. Therefore BNN will be 1 by 1YZA, 1YZB, 1YZC, this thing, okay, into BAN by ZA plus BBN y ZB plus BCN by ZC. This is the expression for neutral voltage, and this voltage is the voltage between this N and this N. So I am finding the voltage of this neutral point with respect to this neutral point. Obviously, this voltage will be 0 in case ZA equal to ZB equal to ZC equal to Z and BAN, BBN, BCN are balanced. And in that case, this neutral voltage is called as zero sequence voltage. We have proved that if the impedances are same, then this becomes BAN plus BBN plus BCN Y3. In case they are balanced, then it becomes BAN plus BBN plus BCN by 3. If the voltages are further balanced, then it becomes 0 also. That depends upon the nature of voltages. So if the impedances are same, even though voltages are unbalanced, this VNN is known as zero sequence voltage. I have explained this point earlier also. But in case the voltage are also balanced, then this becomes 0, which is equivalent to 3-phase 4-wire system where neutral is grounded. Alright, so using these expressions we can find the neutral voltage first, and once we know the neutral voltage we can calculate the current back again from this expression, because this is known to us from here. So this will go back as input here, and then BAN, BBN, BCN are known to us. ZA, ZB, ZC are known to us. We can compute the currents. And once we know the current and voltages, we can find out the powers and power factor for each phase. We can find out the arithmetic, vector and effective apparent powers. But here we are more focused, more concerned about the compensation of the 3-phase unbalanced system. So particularly for this example, we will compute these currents IA, IB, IC and see what is their nature. Are they balanced? Are they in phase with the respective voltages? That we will discuss in the next class by computing these currents using these expressions. So first we will compute the neutral voltage and then solve it for the current IA, IB and IC.